Learning how to predict chemical products can sure be a bear. But before we start, I'm going to teach you a little phrase. Have no fear of ice cold bears. What this saying tells us is things that are diatomic. Diatomic means that it exists as as two. Have no fear of ice cold bears helps us remember what elements on the periodic table are diatomic. They are H2, N2, F2, O2, I2, Cl2, and Br2. Hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine are all diatomic. They exist in the planet stuck together to their cells. Okie doke. Let's keep that in mind before we move on. Predicting products of a chemical reaction is definitely advanced material. But if you can bond and you can determine the type of reaction, then you can definitely predict products. There's a couple of steps that I like to go through for being able to predict the products or what's going to happen in the chemical reaction. So the steps are, first you got to determine what type of reaction it's going to be. I mean, that way kind of guide yourself into the products. You have to crisscross or unswap and drop the ions that are what's given to you. Match them up on the right side. And then you have to take into account, have no fear of ice cold bears. If you're not sure what that is, I'm going to get to that in just a second. And then, of course, balance the chemical equation. So here are some helpful hints about the 5 types of reactions that we're learning and that you're responsible for, things to look for. Alright, so let's run down the list of things to look for when you're predicting a product. If it's a synthesis, it's likely to have 2 reactants on the left-hand side. Most of the time, one of them can be a cation and one of them can be an anion, and typically you're just going to see 2 elements on the left-hand side. A decomposition reaction, well, it's going to decompose into multiple things, so on the left side of the arrow, you're only looking at one thing. A single replacement, those can be a little bit more challenging, but usually it's the presence of a single metal on the left-hand side of the reaction, and that's how you can spot those. Double replacement should look a lot longer than all of the other ones, but it usually has a cation and an anion, a cation and an anion, and that's its format. When you're looking for a combustion reaction, you're looking for some sort of hydrocarbon in the presence of O2. That is its pattern. It will always be that. Okay, so once you can identify what type of reactions there are, and what type of reaction it's going to be, then what you basically have to do is uncrisscross the charges and then recrisscross them and predict what the products are going to be. So let's start with the synthesis. Here I have sodium and chlorine, and the only thing that 2 elements can do is make one compound. Sodium, you know, is a positive 1 charge, chlorine a negative 1 charge. When they come together, they're going to make NaCl, sodium chloride. That's a synthesis. Now, a decomposition reaction, the only thing that that compound can do is come apart into its counterparts, potassium and chlorine. So I know it's going to be a decomposition. But one thing I've got to make sure of is have no fear of ice cold bears. Chlorine will be diatomic. A single replacement reaction has 1 metal, and then usually this other part is some sort of metal stuck to some anion. So the first thing I want to do is I want to uncrisscross the charges. I'm going to have silver and nitrate. Nitrate has a negative 1 charge. Aluminum has a 3+ charge. And do you remember the charge on silver? That's right, silver has a +1 charge. So I'm just going to swap out those metals there, making aluminum with the positive 3 charge and nitrate with the negative 1 charge, crisscross, which will give me Al, NO3, that's a 3, and then all by itself I will have silver. Okay, double replacement, typically a little more challenging, but this is the bonding unit all over again. So I'm going to uncryst all those. There's my silver, it's got a +1 charge, and my nitrite with the NO3 -1. Sodium chloride sodium's got a +1 charge, chlorine's got a -1 charge. And so now I'm just going to swap that cation and that anion. They're both +1. It makes this easy. So this is AgCl. And now the other one, the +1, the -1, NaNO3. All right, and perhaps what's the easiest one, they're often the biggest bear to balance, but the easiest to predict their products are the combustion reactions. So this one right here has a hydrocarbon and O2, and if it's a combustion reaction, 100% of the time, it's going to make CO2 and water, period. That's pretty much what it makes. The best way to do this is to practice. This is a little challenging, I know, but first identify, follow your steps, uncriss-cross. Make sure you account for things that are diatomic. And then, of course, lastly, we're going to balance. Even though I haven't done that with you here, we'll practice that on the next slide. Here you have some practice problems on your next sheet, predicting products, practice. And problems 1 through 5, let's just do a couple of examples. On number 1 here, I noticed that I have 2 elements. Kind of tells me right away that really all I can do with 2 elements is form one thing. My potassium has a +1 charge. And do you know how to determine the charge on iodine? That's right, you go to the periodic table and look at your 1 plus 2 plus. Iodine's in column 17, so it has a -1 charge. So I'm just going to crisscross those and make Ki. Now, if I have potassium and my iodine, which is diatomic, and I make Ki, I need to balance that. And so if I've got 2 iodines on the left, I'm going to need at least 2 there. When I do that, I make 2 potassiums, so I need a 2 there, and there I go. I have it balanced. I've predicted my product and balanced the chemical reaction. All right, I'm going to hop on down to number 4 here. Number 4, I have one thing that tells me that if I have one thing on the left, it's decomposition and it comes apart. So I only have hydrogen and oxygen, so it's going to come apart in hydrogen and oxygen. Have no fear of ice-cold bears, so both of those are diatomic. Now when I want to balance that, that's a little more challenging, right, because it's on one side or the other. So I've got 2 hydrogen on the left and 2 on the right. It's my oxygens that aren't good, so if I put a 2 there, put a 2 there, now I have 4 hydrogens and I need to make 4 there. So, okay, so now 2 oxygens, 4 hydrogens on the left, and on the right, 2 oxygens and 4 hydrogens, so that is balanced. Okay, so here you have a synthesis and a decomposition example. Let's go find a couple more. I'm going to move on down to number 6. Here in number 6, I have a compound with a compound, and I have to recognize that that's polyatomic, right? This is going to be double replacement because there's 2 separate compounds. It's going to come apart in H plus and bromine, which is a negative, and then potassium, which is a +1, and OH on your polyatomic sheet is a minus. So I'm just going to double replace. I'm going to take that cation with that anion, making HOH. And I'm going to take that cation, it's going to go with that one. See, it's more like a dance. Crisscross the charges, K, B, R. And since everyone's a positive to -1 crisscross, it's all balanced really when I look at it here. I've got 2 hydrogens on the left, 2 on the right, 1 oxygen on the left, 1 oxygen on the right, 1 potassium, and 1 bromine. So this is balanced. This is a 1 to 1 to 1 to 1 ratio. Let's hop on down to number 9. Here I have a hydrocarbon and O2. Not always when you see O2 is it going to be combustion, but this just follows the pattern. This is a hydrocarbon, and that is in the presence of oxygen. So it's always going to make CO2 and water. Okay. When it makes CO2 and water, the next thing I have to do is balance, and these can be a little more challenging here. But let's see, I've got 1 carbon on the left, 1 carbon on the right, 2 hydrogen on the left, 2 on the right, 3 oxygens on the left. Oh, so hey, you know what? I'm getting lucky. 1 to 1 to 1 to 1. There, and this is a combustion reaction. All right, so I'm down to single replacement. Can you find one on your sheet that looks like it can be a single replacement? The first one I see is number 10, where I've got lonely little aluminum right here and sodium and carbonate. Carbonate being a polyatomic ion. So first thing I want to do is uncrisscross their charges. Aluminum's got a 3+ charge, sodium with a +1, and if I look up carbonate on my sheet, it's going to have a 2- charge. Alright, so I want to take my cation and go with my other anion, giving me Al2CO3, and I'm going to have sodium all by myself. Now, sodium's not diatomic, right? Have no fear of ice cold bears. It's just the nitrogen gas. So we're just going to leave it like that, all by itself. And now we want to balance. So I've got 2 aluminums on the right. I'm going to put 2 there. 2 sodiums on the left. I got 2 on the right. A carbonate on the left. 3. So I'm going to need a 3 there. Now that gives me a 6 sodiums. So I'm going to go in here and put a 6. And let me see if that's balanced. Alright, it looks good. So my aluminum plus sodium carbonate makes aluminum carbonate and sodium. And it gives me 2 to 3 to 1 to 6 ratio. Alright, that's it for determining and predicting products. That wasn't too bad, right?